So last week, or not last week, but last time we were together, we started to discuss the addition reactions of alkenes. This is where we start to really get into specific types of chemistry and as far as reactions and knowing reagents. Remember, my suggestion is to focus on reagents and think about what they do, because once you figure out what a reagent does, then you sort of don't really have to brute force memorize these reactions. But at the same time, we're in Organic Chemistry 1, and there is some benefit in brute force memorizing reactions because you don't really have a good feel for what's going on. So for right now, I would take both approaches and just sort of try to memorize the reactions, but really looking forward in the future to get a good feel what's going on with these reagents and what those reagents do. So we introduced those addition reactions to alkenes. We talked about several different reactions. We did the addition of HBr, we did the addition of water, we did the addition of X2, we did the addition of H2, and what else did we do? We did addition of water in several different ways. I think there were 3 different additions of water. And so where we left off yesterday was the addition of Br2, and so that's where I want to pick up, and I'll just I'll kind of re-go over that one, and then once we go over that one, that starts the conversation about Halohydrin Formation, which is a similar reaction, or it works by the same mechanism. But instead of adding Br twice, it adds Br once, and then it adds water after that, or it adds HO, forms an alcohol group after that. So let me switch over to my screen. All right. So we started here yesterday. This is where we were. We were talking about the addition of Br2. And this adds Br to across the double bond. And there were a couple of things that we had to consider, that this was anti-addition. And the other thing we had to consider was the mechanism. And the reason that we had to consider the mechanism was because that explained the stereochemistry. It did involve this nucleophilic attack to the Br, but it also involved another one back into the double bond. And so that created this cyclic bromonium ion intermediate. And that's why we had anti-addition because the bromine can only add to one side. And now, of course, when it comes to double bonds, it doesn't really matter that when it comes to molecules that when it comes to alkenes that get formed that are not rings, or that don't have stereocenters, then it's not such an issue, but it becomes a lot more important when it has a ring structure. Another time that it's important is when you have the difference between cis and trans alkenes. So if you think about how this works out, it's still going to be anti-addition. Let's see. It's still going to be anti-addition. But for the sake of explaining here, if we rotate around this single bond to put it in the same perspective, we actually end up with a compound that looks like this. And this one is meso. So this one is not. This one is not meso. And so there is this consideration to be made when it comes to the starting geometry, or the starting stereochemistry of the alkene. We talked about the ring structures and how it's particularly important there, but there is going to be some minor considerations for the starting geometry of the alkene, so you want to be sure to keep an eye on that as well. All right, using that same reaction, or that same mechanism, here's the next reaction that we're talking about. This is Halohydrin Formation. We just finished halogenation. This one's Halohydrin Formation. It involves the same sort of reagents, the same starting material, the same Br2, but now we're going to do it in the presence of water. It adds bromine to one location, but an OH to another location. So this is a halohydrin. So here's your halogen part. Here's the water part. That's what the hydrin is. And so you get a Br on one side and an OH on the other side. But take a look at what the regioselective outcome is. From a regioselective standpoint, a regiochemical standpoint, the OH adds Markovnikov. And if we think about it, we got to know the mechanism, but good thing we already know this one. And the mechanism can explain why it adds that way. So you're still going to form a cyclic bromonium ion intermediate. So you still have a Br three-membered ring. And now you have your water coming along here. So what I'm going to do is I'm going to add a substituent to see to show what's going on with the regioselective outcome of the OH addition. Remember that this can have a resonance structure where you can, and I don't want to say it's actually a strictly resonance, it's a strict resonance structure, but you can show this idea that the bromine can be attached here and leave a cation there, or that the bromine can be attached at the other spot and leave a cation there. Well, remember that the truth is somewhat in between. And at the end of the day, the preference would be to have the most positive charge at the more substituted location. And so which one of the quasi-resonance structures is more important is this one. This one's more important than this one because the positive charge is in the more substituted location. So the mechanism should properly be shown this way, and that gets you to this step. I'm going to go ahead and make it and then typically we can show either water or bromine coming off to do this proton transfer. This is positively charged. You do need the only difference in the mechanism is that you need a proton transfer to finish it out. And that gets you the halohydrin. So it is essentially the exact same mechanism. It is, I'm sorry, I'm having a senior moment again. It's happening a lot these days. It is a situation where you're going to add the water. The water's going to add Markovnikov. The reason it's going to add Markovnikov is because the positive charge is more predominantly on the more substituted location than it is at the least substituted location. We still have anti-addition. It's still anti-addition. So properly, when I show the product, I should show it like this and say I also have the enantiomer. So you get both versions and the of the molecule. All right, let me pull up make sure I got my participant and chat window up so I can see chat if it goes. All right, any questions about that one? Pop it in the chat. So again, it's the same mechanism before. It's just instead of having Br2 by itself, you're doing Br2 in the presence of water. The OH adds Markovnikov, still anti-addition. All right, so the next one is dihydroxylation. And we're going to talk about several different types of So the question is asked, do you have to specify 1 Br2 and 2 H2O? So no, that's a good question. It's for halohydrin formation, it's not a two-step reaction. It's just a one-step reaction where you have, in the first case, when it's just bromination, you have bromine without any water present. For halohydrin formation, you have bromine in the presence of water. So when I write water under the arrow, I could have just as easily wrote it above the arrow by using a comma after bromine and say Br2, comma, water. It just means that they're both in the pot together. It's specifically not a two-step reaction. So that's a good question. All right, so so we're going to talk about two different types of dihydroxylation. We're going to talk about anti-dihydroxylation, and we're going to talk about Syn Dihydroxylation. Right now, we're going to talk about anti-dihydroxylation. It always surprises me that we don't talk about this reaction in and of itself, that we don't talk about epoxides until organic chemistry 2. But if I react an alkene with a peroxy acid, and RCO3H looks like this. It's a carbonyl group that has a peroxide on the other side of it. It's almost like a carboxylic acid, but it's actually a peroxide. So that's RCO3H. And so if you react that alkene in the presence of peroxy acid, you form an epoxide. So it really, I don't really understand why we don't talk about this particular reaction in organic chemistry 1, and we save this one until organic chemistry 2, but it really is this first step. We form an epoxide. Now, the way that I'm going to show you this reaction is like this. This is how I would write it on the reaction board. Now, one of the things that we're not able to do is be in the lecture hall where I would have one board off to the side where I'm just writing the reaction down. So in other words, this is the information you would put on a note card. And that's what this is down here at the bottom of the screen. I would do 1 RCO3H, and the second part would be acid, H3O+. And so this one is a two-step reaction, and we typically don't talk about it in this sense that, oh, there is an intermediate epoxide, but I think it is important for two reasons. One, because the reaction shows up again in organic chemistry 2, and also it explains the stereochemistry of the reaction. Now, this is a mechanism that you don't have to know, but it is helpful to understand some of the different properties of this. Ultimately, this is going to be anti-dihydroxylation, and so I'm going to have an OH here, an OH here, and they're going to add on opposite sides of each other. So I'm going to show this in the ring, and in the ring, when we do acid, we end up with a trans diol. Of course, you get the enantiomer. So there really isn't a regioselective consideration to make because we're adding two of the same groups, so they're both going to add across the double bond. The question is, well, what's going on? Why is it trans? And at the end of the day, what you have is you get this epoxide. And again, this is another example of a cyclic intermediate determining the outcome of the reaction. You have the epoxide pointing on one side of the ring. In this case, I'm showing it pointing down. When you have the acid come along, it protonates the epoxide. It forms a cation, and now water comes along and attacks. Well, again, we have the same sort of situation. When you have the water that comes along and attacks, it can only attack from the less sterically hindered side, and so it attacks from above or below, depending on whatever the opposite of where that epoxide was. And so you get an OH here. Let's make this on a wedge. Let's put this on a dash. You get a water here. And then, of course, you have to come along and deprotonate it. And that's what gets you your product. So let's kind of review that. I don't expect you to know how the epoxide forms. But if I show you an epoxide and an acid and suggest to you, well, can you explain the stereochemical outcome? You should be able to say something to the effect that the three-membered cyclic epoxide prevents attack from the same side, and it promotes backside attack. And that backside attack is what explains the fact that it's anti-dihydroxylation. Let's see. And so what are some of, so I just want to make sure that we understand this is the peroxide that we use, but another way that we see this peroxide is in the MCPBA as an acronym. And this means meta, so actually let me draw it over here. This is meta-chloroperoxybenzoic acid. So it's in benzene. There's a chlorine in the meta position. This is what that peroxide looks like. And so what you see sometimes is just the abbreviation MCPBA, or you could see RCO3H. You'll see either of those two possibilities. So I want to just kind of give you a warning about that, especially when you're coming to do the homework. I would like to say that I did notice that nobody's really worked on the Chapter 8 homework. No one, and essentially no one has worked on the Chapter 7 homework. So with an exam coming up in just about a week, I suggest that situation change. So enough of that. No more of that gloom and doom. So can you repeat what you said about backside attack? Yeah, so Shelley, what I'm saying about backside attack is this. If I have an epoxide, which is a three-membered oxygen-based ring, that means that I can't, or that it's not favored to have the water attack from this same side. The water instead attacks from the other side of the ring. And this is essentially the same idea as backside attack. And so this explains the fact that it's anti-dihydroxylation, that that the one OH group points in the opposite direction as the other OH group in the final product, because this Syn addition isn't favored because of the steric hindrance in that cyclic intermediate. Okay. And so hopefully that helps. What I want to do then is just point out that we've talked about several different intermediates. We've talked about this one just now, a protonated epoxide. We've talked about a bromonium ion. And we, even if you remember way back in the beginning, we talked in oxymercuration, demercuration, we talked about a mercurium ion. So remember that I didn't specifically ask you to know the mechanisms behind any of these except for this one, and halohydrin formation and bromination or halogenation. But for all of them, you should definitely keep in mind this key point, that it involves this cyclic intermediate. And this cyclic intermediate produces anti-products. And so remember that knowing the mechanism or knowing the details behind some of the intermediates in the mechanism really does help explain the stereochemistry. We'll see that in these three examples when we have three-membered cyclic rings, that we always get this anti-product, and there'll be other types of cyclic intermediates that will lead to cis products, and we'll see about that in just a second, because that was anti-dihydroxylation. But what we want to do is we want to do Syn dihydroxylation now. So Syn means the same side. Now, at the end of the day, it's a similar reaction. And if I show it on a molecule where the stereochemistry isn't important, then you essentially end up with the same product, right? Because if I have something where there's only one stereocenter, or there's no stereocenters that are formed, then you don't really have to worry about that particular product. But at the end of the day, this is Syn dihydroxylation. And so we have to think about what would happen if it were on a ring where that actually is important. And so if I were to think about what's going on here, in step one, we have osmium tetraoxide. And osmium tetraoxide is an osmium atom that's got 4 bonds to oxygen. And at the end of the day, it also makes a cyclic intermediate. But this cyclic intermediate has 5 different atoms in it. And because, so what at the end of the day, these 2 oxygens come from the osmium tetroxide, and they add at the same time. So this is an osmate ester. And if you think to yourself, well, if I'm doing osmium tetroxide, it's an osmate ester, and that osmate ester is where the oxygens come from, then that means that I end up with a product that has the oxygens on the same side. And the reason that they're on the same side is because in this intermediate ester, the oxygens are coming from the OSO4 and they add at the same time. So I attach, I can show some sort of electrons here. To form this intermediate ester. Now, I don't expect you to know the mechanism. Yeah, what is that at 1? Yeah, osmium tetroxide, OSO4. I don't expect you to know the mechanism, but I do expect that you have some idea that you form a cyclic intermediate. It's a 5-membered ring, and the 2 of the 4 oxygens on OSO4 attach to the ring at the same time. And this is what explains the Syn addition. So it's still dihydroxylation, but the 2 OHs add on the same group. Now, there's another reaction with a very similar reagent that has this exact same stereochemical outcome. And instead of using OSO4, we use KMNO4. So it's same starting material, same product as far as our simple view is concerned. It's Km potassium permanganate with sodium hydroxide and water. This is not 2 steps. This is only 1 step. But at the end of the day, you have a similar situation. The oxygens that are in the molecule come from the manganese tetroxide. They come from the permanganate. And it forms the exact same type of intermediate. Once this thing gets reacted with sodium hydroxide in the same pot, you also get Syn addition. So what should you be on the lookout for? You should be on the lookout for KMNO4 or OSO4. Those 2 reagents should key you in that there's Syn addition. Not only is there Syn addition, there's Syn addition for the same reason. It's about this cyclic ester. Now, in the situation with OSO4, the osmate ester could be isolated. That's why it was 2 steps. This one is not isolated. It happens in 1 step in the same pot. Okay, so what I'm gonna pause real quick right there. See if anybody has any questions on that. So we just did 3 reactions. Actually, we did 4. Okay. All right, so that's it for dihydroxylation. This is one of my favorites. This next one is called oxidative cleavage. So if I react O3 in step 1 and DMS in the 2nd step, just dimethyl sulfide, then it actually comes along and it breaks this bond. When it breaks this bond, it inserts oxygens on either side of it. So what I think students easily get a handle on this one, because for a simple view like this, if I just draw a line across the double bond and imagine splitting them apart, and then drawing in oxygen on either side of that double bond, I have an easy solution to the problem. There isn't a mechanism that you need to know here, but there is something that you should think about when it comes to so let's try this. When it comes to doing these problems, they're not exactly, in other words, they can be complicated. So let's take a look at an example. What was this? What was the starting material for this? It's bicyclic. What's the starting material for this? It's bicyclic. So this is a challenge. If I were to say, I formed this, and this, then all you would do would be to take that double bond and put these two groups on either side of it and say that was my starting material. But it's a little bit more complicated in this structure. I'm giving you a hint that it's bicyclic. And so let me erase a few things and let's take a look at how I might approach solving this particular problem. One of the things that I would do is I would say to myself, I would want to count the carbons. And so I have 1, 2, 3 carbons there. If I were to have connected those 3 carbons with this double bond and this double bond, that would have been a 4-membered ring. So that's probably not the actual way to go because a 4-membered ring in an alkane is not favored. So a 4-membered ring with an alkene is definitely not favored. So let's continue to count carbons though. I've got 1, 2, 3, 4, 5, 6. I could do a 6-membered ring that has a double bond in it. Well, what about this? Now let's take a look at the other one. So maybe it was this one and this one together. Well, what about the other set? This was 1, 2, 3, 4, 5. Oh, so maybe it was these two together to do a double bond. So I had a 5-membered ring fused to a 6-membered ring. And so let's see how that might have looked, how that might have worked out. What I want to do is I want to color code them. So we said it could have been this 6-membered ring here. So let's draw 1, 2, 3, 4, 5, 6-membered ring. At this point, since we haven't added anything else, the location of the double bond is somewhat arbitrary. So let's put it here. Actually, let's put it here. Now we have to sort out where this other thing was attached. So this, now I want to put it in a different color. This and this are the 2 carbons that have the double bond. They're the ones that are in purple. And so I would count over. I would say there's 1, 2 atoms in between one of them, and that starts the next 5-membered ring. So I can say, all right, 1, 2 atoms starts the next 5-membered ring. And so if I were to draw that 5-membered ring, Let's draw it in green. It's 1, 2, 3, but it also includes this bond. They share the same bond. And so that must be this bond here. And so it's 1, 2, 3, 4, 5. And so this atom and this atom are the same. And so that must mean that this is where the double bond is. So I know that's a little, oh, let me get somebody in here. So that's a pretty intense example, but I want to give you a quick idea of that it can be fairly simple and straightforward, or it can involve a little bit more of an analysis. So at the end of the day, the reaction is fairly simple. Double bond, O3, step 1, DMS, and step 2. You get, in this case, you get two of those. But this can really get complicated really quickly, especially when you get into a big product like this that you really have to do some thinking. So let me pause a beat real quick right there and see if anybody has any questions. Okay, well, there's some good news. And the good news is that's the last reaction. That's the last reaction in chapter 8. We're almost done with chapter 8. How many did we learn? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 reactions. There's 12 reactions and 10 different products. 12 reactions, 10 different products. So let's think about this. So the next 11, we learned 12. I think it was 12. If you count maybe you're not counting the addition of H3O plus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. I'm counting 12. Take a look at the slides on, there's slide 897 that has a nice little review of all the different reactions. What I want to do is I want to think about, at the end of every one of these chapters from now on, or the end of every discussion of a particular set of reactions, what we're going to talk about is how do we incorporate those reactions into retrosynthetic analysis, into a synthesis problem. And so let me give you an example. What if I have something like this? And I say synthesize this. This is an example of a synthesis problem. When I'm talking about using both methods to memorize these reactions, learn the reagents, really that's what you should be thinking about with your future in mind, but getting through it in the immediate future, in the next few weeks, is brute force memorization and using index cards. Well, on one side of the index card, you would have A goes to question mark with a particular reagent. But on the other side of the index card would essentially be a one-step synthesis. It would be A goes to B, and then what is the reagent? This is an example of a one-step synthesis problem that I provided you at the top of this screen. You have a 6-membered ring as a starting material that has a double bond in that position. You want to add an OH group. So what are the things that you have to think about? What you need to think about is, well, what did I do? I added an OH. So immediately, of the 12 reactions that we know, that should eliminate, I think, mostly 8 of them, at least 8 of them, maybe even 9 of them. So I added OH. The next thing I want to do is, well, what was the stereochemistry or the regioselective outcome of the addition of OH? Was it Markovnikov? Or was it anti-Markovnikov? And if you think about the location of the double bond and where the double bond was and where the OH is, you see to yourself that the OH added at the more substituted position. So now you're thinking to yourself, that's the Markovnikov addition of OH. So now you had 12 reactions plus all of the reactions from elimination and addition, substitution, but this isn't a substitution reaction or an elimination reaction. So you've already eliminated all the possibilities from chapter 7. It's only the possibilities from chapter 8, only the possibilities from the additions of alkenes. You've taken all 12 of those reactions and now you've narrowed it down to 2. You've got the Markovnikov addition of OH, and so that gives you 2 possibilities. Hydration from an acid catalyzed hydration, or that means you could have also done, what's the other one? Oxymercuration, demercuration. And so the last thought to have is, what are the 2 outcomes of these possible reactions? Remember that in a hydration, you should be thinking with acid catalyst, you should be thinking to yourself that the intermediate forms a carbocation. And I have to worry about rearrangements. In this case, if I form an intermediate carbocation from adding H3O plus, I form it here, and that's already the more substituted location. So there's no problem using acid catalyzed hydration in this example. You could also use oxymercuration, demercuration. That would be a fine answer to this synthesis problem. Remember that in essentially every synthesis problem, there are more than one possible correct answers. Now, from a synthetic point of view, actually in the lab, it's much cleaner and much easier to deal with water and acid rather than mercury. But in the theory part, in lecture, either of these answers would be accepted. If you worked in a lab and your boss said, do this, your boss would say, why did you spend $100 on a mercury reagent when you could have used a $4 acid reagent? So that's a whole different thing. But the reason why I point out the fact that you have to consider the mechanisms and what you have to worry about as far as the intricacies of the mechanism. What if I had a reaction that was like this? Let me make a slight alteration to the starting material and the product. So now we come up with the same 2 conclusions, that I added OH and the OH added Markovnikov. So that then still eliminates the 12 reactions. It boils it down to 2. However, the problem is now with hydration, I have to worry about rearrangement. And if all of a sudden now what I'm going to use is I'm going to use this same structure up here. If I came with this same structure and formed an intermediate carbocation there, I would actually get a rearrangement and it would lead me to this product, to the original product, through a hydride shift. So that means that this reaction is actually no longer a correct answer. The only correct answer for this solution would be oxymercuration, demercuration. That's the only reaction that would lead to this alcohol at the secondary location. If you did acid catalyzed hydration, you'd get the hydride shift and you'd still end up with the tertiary alcohol. Okay, any questions about that one? So what we're doing right now is we're starting to think about synthesis, and we're starting to think about how do we approach synthesis problems. Okay, so that's an example of a single step synthesis. But at the end of the day, one of the things we're going to have to do is think about synthesis that involve more than one step. What if I said, how do I synthesize this molecule? So you're essentially still going to approach it the same way, in that you want to look at the product and see what you have. In the product, I have a halogen. So maybe I added 1 Br. It looks like it's in the most substituted location. So I'm thinking to myself, perhaps it was added Markovnikov. But the problem is that there is not a single step that moves, that we know, there's not a reaction that we know that takes a bromine on one atom and moves it to another atom. We don't know any such reaction. So that means that there's more than one step involved in this synthesis problem. And this is where the idea of retrosynthetic analysis starts to help. How could I have made this product? The idea behind retrosynthesis is to think backwards. Do you know a reaction that adds bromine in the most substituted location of some sort of reagent? And you should be thinking to yourself, I do know that if there was a double bond here, that I could add HBr to that double bond, and I would get a bromine added Markovnikov in the most substituted location. In other words, I can do an addition reaction of this alkene to get to that product. This is the idea behind retrosynthesis, is that you take the product and you think back one step. What could I have made that product from? The idea is, and there's this, I told you before, there's this little leap of faith that you have to make. You're hoping that the faith that you're making is that if you continue to think back one step at a time, you'll get to your original starting material. And so the question is can you get from here? If I think back one step, how do I make a double bond in this location? Can I do this from the starting material? And so now I'm saying yes. Now, not only can you do this from the starting material, but I'm also bringing back the reactions from chapter 7, the reactions from the substitution and elimination chapter. You can make this double bond. Well, how did you make this double bond? Would this be a Zaitsev or Hoffman product from eliminating that bromine? Well, it's the more substituted double bond, so it's the Zaitsev product. And so I would use a base, but I would use a small base. So something like sodium methoxide. Yeah, it's Zaitsev. And so this is the solution to this synthesis problem. If I give you this synthesis problem like this and say, form this molecule, the solution is this for step 1. Sodium methoxide. Step 2, HBr. That's the answer to this problem. It does take 2 steps. The first step eliminates the bromine, forms the double bond. The second step adds the bromine back in a Markovnikov fashion from the addition of the double bond. We know that we have to use a small base because of the fact that it's a Zaitsev product and not a Hofmann product. Okay. All right, so let's think about this. Let's do another example just like that. What about this starting material? How could I accomplish this synthesis? How could I accomplish this transformation? Well, really, we're going to approach it the exact same way. Let's think about the product and let's think about what there is on this product. On the product, we have an OH, and it's at the end. And this kind of indicates that if it was added, then it was added anti-Markovnikov. And let me just make sure that I'm giving you I'm contrasting that. The starting material has an OH in a more substituted location. So we wouldn't have added an OH in a Markovnikov fashion because we would end up back in the starting material. So what we're saying is we did have an OH group and we added it anti-Markovnikov. So this immediately takes all of the reactions that we know from addition and it reduces them down to one single reaction. There's only one reaction that we know that adds OH in an anti-Markovnikov fashion. And that's hydroboration oxidation. Then we have to say to ourselves, well, where would the double bond have been in order to add the OH there? Well, remember that the OH adds across a double bond. And if it's going to add in the least substituted location, then the double bond must have been between those 2 points. So that tells us what the starting material was in this particular step. That was the starting material. Okay, well, so what about this particular addition? What about this particular double bond? How could I have formed this double bond? And move it. Well, now I want to start to make some considerations about this product. Well, let's think about it. It's an alkene, and it's got a double bond, but the double bond is actually in the least substituted location, so it's a Hofmann alkene. All right, so that's going to lead us to some considerations. Let's take a look back at the original starting material and just ask ourselves the question, can we make a double bond from eliminating an OH? You should hopefully be saying to yourself, oh, sure, I can take an OH and do concentrated H2SO4, and I can make a double bond. But what kind of product does this reaction form if you think about it from the mechanistic standpoint, back from elimination and substitution? This should always form the Zaitsev product, and it should always form the lowest energy alkene. So I can't directly go from here to there. It's not possible. So I have to do something in the intermediate. How do I get a Hofmann product? Well, I have to take a leaving group. It has to be a good leaving group. And I have to use a bulky base. So the idea that it's a Hofmann product leads me to the knowledge that I had a bulky base, so T-butoxide. Let me make that a little bit clearer. So tertiary butoxide. So I know that I have a bulky base, but I can't eliminate a high OH with a bulky base. I can only eliminate OHs with acids. But what could I do to eliminate a functional group? What could have been a good functional group at that point? Well, if I had a really good, and I'm just going to put a simple leaving group here. If I had a good leaving group in that location, then the elimination would proceed in the fashion that I described with the tertiary butoxide. Now that I've identified that this needs to be a good leaving group, I start to think now, is there a way to transform the OH into a good leaving group? And then what would that good leaving group look like? Now I really do need to bring in my knowledge from elimination and substitution reactions. If I react to an alcohol with a tosylate chloride and pyridine, then I form a tosylate ester, and tosylate esters are excellent leaving groups. And so I can accomplish the transformation in this manner. It is a multi-step synthesis that involves a little bit of consideration, but really what you have to know is you have to know these reactions. I can teach you how to think backwards, and I can teach you about the considerations that you have to make at each step. In this first step, we thought that the product was an OH group. The OH is looking like it's at the end of a carbon. If it's at the end of the carbon, that's sort of anti-Markovnikov. That kind of gives us the idea that only we can do is hydroboration oxidation. Once we have the idea that it's hydroboration oxidation, then we can come up with the starting material that would work with hydroboration oxidation. I can teach you then, once you have that material, that you can say, okay, it's an alkene. It looks like it might have been a Hoffman product. And now, but this is where the rest of it is where your reaction knowledge came in. Reaction knowledge told you hydroboration oxidation. Reaction knowledge told you bulky base. Reaction knowledge told you that I can turn an OH into a good leaving group and turn it into a tosylate chloride. Without that reaction knowledge, you're not going to be able to solve these problems. And so at the end of the day, the answer to this particular synthesis problem would be step 1, TSCl and pyridine. Step 2, tertiary butoxide. Step 3, BH3 THF. Step 4, sodium hydroxide and peroxide. So this is it's a 3-step synthesis, although the answer looks like it's 4 steps because one of the transformations actually is a 2-step reaction. So what I want to do is I just want to stop right there, take a beat, and kind of see if anybody has any questions about that one. All right, so there's another thing that I sort of want to talk about here. All right, here's another synthesis that we need to think about. What if I have this? Let's do this. So this is the starting material. I got a double bond in the more substituted location, and the product is a double bond in the least substituted location. So let's approach this with some of the same retrosynthetic planning that we've been doing. So what's going on in this product? The product is an alkene. Right away, this should be telling you something. You only know one set of reactions that leads to alkenes, and these are elimination reactions. Well, what was the alkene? The alkene is, if you think about it from a regioselective or stereoselective consideration, it's a Hoffman. It's a Hoffman alkane. So that should be telling you again, bulky, sterically hindered base. All right, now that you've made the consideration that you're going to form an alkene by doing an elimination to get a Hoffman product by using a bulky, sterically hindered base, now you can start to think about what are the possibilities for the different types of reagents that you could have used in order to accomplish that transformation. So let's think about it in terms of all of the possibilities. One thing I could have had was a bromine in this location. If I use potassium tertiary butoxide, then I'll get the Hoffman elimination from there. Another thing I could have had was, I could have had a bromine here, and I can use any base to get to that product. Okay, so let's continue to think about it. How could I have made this one? And so this might be an analysis, the thought process that you go through. And I want to do this for a particular reason, as I want to illustrate this concept that you can easily walk yourself into a dead end, but I want you to be able to identify the fact that you're in a dead end so that you know that one of the possibilities isn't something that you should continue to think about anymore. Well, how could you so let's continue to think backwards along this path and say to myself, well, how could I get a bromine in this location? Well, I would say to myself, okay, I've got a bromine. It's at the end. So that means it could have been added, and it could have been added anti-Markovnikov. You only know one reaction that adds bromines anti-Markovnikov, that's HBr, in the presence of peroxide. And now let's think about the starting material and what it would have had to be. Well, in order to add a bromine anti-Markovnikov in the locations, there would have had to have been a double bond between those two red dots. So that means that the starting material had to look like this. Well, what's the deal here? This and this are identical. So you see that you're sort of going in a circle along this path. And so what that should indicate to you is that this path is not valuable. You shouldn't think about this path anymore. And you shouldn't think about this as a probable previous reagent, because as you continue to work backwards, you seem to be going in a circle. And so that's often going to happen, and it's okay to have that happen. But what you need to do is you need to acknowledge that that happened, and you need to say to yourself, that's not helpful. That's not helping me solve the problem. But what that does do then is help you say to yourself, okay, that must mean that this is a good place to get back to go back to this concept of this particular addition, and let's think about that one. Okay, so now I'm thinking about this reagent or this product, and I'm saying to myself, all right, I have a bromine, but instead of being attached at the end, it's attached it's at a secondary location. And so Markovnikov or anti-Markovnikov depends on where the double bond is. If the double bond were between here and here, it would be a Markovnikov orientation there. But again, having the double bond in that location is back to that starting material, so that doesn't help. We could have had an anti-Markovnikov We could have anti-Markovnikov formation or addition of that bromine in that location. If the double bond were between the two yellow dots now, we could do anti-Markovnikov addition of the bromine in that location, and that leads us to a new and unique reagent. And so that seems like it might be a good step. So now what I'm going to say is it's in a secondary location. We decided that it was anti-Markovnikov. And that would mean that I had a double bond between those two yellow dots. And so that's the starting material. And so that must have been HBr and ROOR. And look, I've now solved the problem because I've just worked it backwards and I ended up at the starting material. This is a perfect example of how retrosynthetic analysis does work. It really is a good way to get things moving. It really does help in organizing your thoughts. But at the end of the day, the bottom line is you're always going to struggle with synthesis unless you know the reactions. There's nothing that you will never be an amazing synthesis problem solver unless you know these reactions. Whether you know them because you have intimate understanding of the mechanisms, the possible intermediates, and how that produces all the different products, which also means thinking about these reagents, or you use flashcards and you memorize every single little thing. Whatever that case is, that's how you do it. So here's what I'm going to do right now. We've still got a bit of time, and so what I want to do is I want to stop the recording because that's a hard